In our last unit, we were looking at the law of conservation of energy, and as you recall, the law of conservation of energy says the internal energy of a system is equal to the heat transferred to the system minus the work done by the system. You could also say plus the work done on the system. It would be equivalent. Now, what is internal energy? Well, internal energy is the sum of the kinetic and potential energy of the internal pieces. So kinetic energy of the particles plus potential energy of the particles, and that gives me the internal energy. Now, for liquids and solids, there is some potential energy to consider. Remember, potential energy is due to an outside force acting on them. So this particle has potential energy because there's an attractive force between it and other particles around it in a liquid. And in a solid, there's potential energy between these particles and solid because there's forces of attraction holding them in place. But in a gas, we consider the particles to be moving so fast and collide with perfectly elastic collisions so that there are no attractive forces between them, which means there is no potential energy. So for a gas, the change in internal energy, or in just the internal energy, is really directly proportional to the kinetic energy, or equal to the kinetic energy of the gas, which is directly proportional to the temperature of the gas. So temperature is directly related to the kinetic energy or the internal energy of a gas. Now, what we want to do is we want to explain how we can use this rule to try to figure out what the difference is between heat and work and change in internal energy and everything that's happening. So to do that, we're going to examine a system. And this system consists of a gas that is in a sealed container that has a piston on top that can move up and down. Now let's say we keep this gas at a constant pressure. So I'm going to say the pressure is constant. And I'm going to go ahead and add some heat to it. Okay? Now if I add heat to it but the pressure remains constant, that means that these particles are gaining energy. They're going to collide and hit more often, and that's going to push this piston up, and that means work is done on the piston. Now remember, work is equal to force times distance. Okay, how much work does this piston do in moving, or does the gas do in moving this cylinder a distance, or the piston a distance d? This is actually not so complicated. Since we're holding pressure constant, we know that pressure is equal to force over area. We know that work is equal to force times distance. So in terms of pressure, what we have is work is equal to pressure times area times distance. But the distance that it moves times the area is actually the change in volume of this gas. So what I have is the work done by the gas is equal to the pressure times the change in volume. Now, since I'm holding this at a constant pressure, it's easy to graph what this looks like on a pressure versus volume graph. So over here I have pressure, and down here I have volume. And arbitrarily 0. So this thing started with some volume, VA, and some pressure that was not 0. Okay? And that pressure remained constant as we increase the volume to over here, volume B. And so the work done, since it's pressure times change in volume, is given by the area under this pressure times volume curve. Okay? So we did this for a constant pressure, but it's true even if the pressure isn't constant. So if we were looking at something that was more like Boyle's law, where the pressure looked like this, because the temperature remained constant, we could still say that the work done is equal to the area under the curve. It's just harder to find that. We have to use calculus or estimate, or maybe perhaps use an average pressure value to estimate the work done. So we can use the fact that the area under a pressure volume curve is equal to work to help us when we analyze some situations. So that's something to keep in mind. Area under a PV curve is equal to work done. Alright, so we're going to use this relationship to analyze what this equation really means. So we're going to look at 4 different thermodynamic processes and figure out what's going on in terms of pressure, volume, temperature, and work. So the first process we want to take a look at is a thing called an isothermal process. Now, iso means same, thermal means temperature. So what this means is things are happening at a constant temperature. Now, if this is happening at a constant temperature, we assume any changes in the system are happening slowly so that the temperature has a chance to be in equilibrium with its surroundings. So, what we consider, if we have my piston still, my cylinder of gas and the piston on it, okay, any changes in the system are done so slowly that the temperature of the heat reservoir around it is able to keep this in equilibrium with itself. So isothermal means constant temperature. Now let's go back to our first law of thermodynamics, conservation of energy. Change in internal energy is equal to the work or the heat added to the system minus the work done by the system. Now, if we're keeping this thing at a constant temperature, remember that means that the internal energy can't change, because the only internal energy of a gas is kinetic energy, and if the temperature doesn't change, the kinetic energy doesn't change. So what I have for an isothermal thing is that the change in thermal energy is equal to 0, which means 0 equals Q minus W, which also means that Q is equal to the work done. Now, so let's think about what that means. If I put this thing in contact, well, let's say it a different way. Okay, let's say that I have this cylinder of gas, and this piston starts to move up, but the temperature isn't changing. Okay? So the internal energy isn't changing. That means all the heat that goes into this thing is not raising the temperature of it. Instead, it's expanding the volume of it. Okay? It's increasing the volume, and that means this thing is doing work. Now, we know that we can figure out how much work is being done if we can look at the pressure versus volume graph. Now, in order to make this graph, we have to look at this equation. Pressure times volume is equal to the number of particles times the gas constant times, so this is actually moles of particles, times the temperature, T. And that has to be in kelvins. Well, if our temperature is not changing, then the pressure times volume is also not changing. So this is equal to a constant for an isothermal system, which really means PV equals some constant K, which means our graph, our pressure times volume graph, is just an inverse relationship, and it looks sort of like this. I just randomly picked that. So that means if we started here at A, and some process happened and we went to B, some isothermal process happened, you can see that our volume increased, our pressure decreased, and in order to get that to happen, we had to add heat into this thing, but instead of that heat actually increasing the temperature and increasing the energy, it actually was used to do work and raise this piston up off the cylinder. And the work that it did is equal to the area under here. It's also equal to the heat that it gains. So in an isothermal thing like this, we can see how much work is done. Now, this whole thing could have been done at a higher temperature, and if it had been done at a higher temperature, this curve would look exactly the same, except it would be shifted up. Okay? So if we want to get the same amount of work done at a higher temperature, then, and this is 0 pressure, then the work done would be more. Okay? And the energy change, the heat added, would be more. So there we have an isothermal constant temperature expansion that does work. So in this thing, all the heat, all added heat, does work. That's all that means. So that is an isothermal expansion. Now another expansion, or another thermodynamic process we can take a look at, is a process called an adiabatic expansion. Okay? Now in adiabatic, no heat is transferred. Now this seems a little bit weird if we're talking about a thermodynamic process And if thermodynamic is, thermo is thermal energy and dynamic is motion, so why would we have a thermodynamic process that means no heat is transferred? But that doesn't mean we're not changing thermal energy, the internal energy of the system. So again, I have my gas enclosed in this cylinder and a piston that's free to move. Now, if no heat is transferred, that happens in two ways. Either anything that moves this piston does it so rapidly that heat doesn't have a chance to leak out or leak in, or this is a very well insulated system. Generally, it's the speed thing, but you could insulate something pretty well. All right, so I have this piston, no heat is transferred. If we look at this in terms of our equation, change in internal energy equals heat added minus work done. But we're saying no heat is added or lost at all, so Q is equal to 0. That means the change in internal energy is equal to, and I'm going to change this up a little bit. We subtract this work because this is equal to the work done by the system. I want to look at the idea of work done on the system, which would be positive, right? So if I do work on the system and I smash this piston down really, really hard, what happens? Well, I just did a whole bunch of work, and all that work caused a change in internal energy, a positive change in internal energy, which means it got warmer, okay? So in an adiabatic process, work done on the system, leads to, or causes, let's say it that way, causes internal energy to increase, and that means higher temps. However, if the system does work on something else, so work done by the system, okay, so imagine that this gas in here all of a sudden exploded and pushed that piston way, way out. Okay, so work done by the system then is actually going to cause a decrease in temperature. So work done by the system causes the internal energy, just U, to decrease, which means the temperature is going to be lower temp. Okay? So those are two fairly important processes that happen in thermodynamic cycles. In a thermodynamic cycle, you go through some changes where the temperature, pressure, volume might change, but they all eventually end up back at the same spot. The first one we looked at, where we actually came up with this rule that told us that the work done is under this pressure volume curve. Since we held the pressure constant, this is called an isobaric. Okay? And in an isobaric change, let's think about what's happening. Work is being done, but the pressure is remaining constant. So if we think about this, the work done on the system is actually used to increase the volume of the system. It's used to expand the system. Now there's one more thing I want to take a look at, and it's called an isochoric change. So if we go to isochoric, okay, the other term that you can call this, and it's sometimes referred to, is isovolumetric. So this is constant volume. So let's think about what happens to this thing if I hold the volume constant. Okay? So this piston is no longer allowed to move. So if this system isn't allowed to move, and I've got my gas particles in there, and the change in internal energy is equal to Q minus W, okay, what happens if heat is added to this system? Well, if this piston cannot move, no work can be done, right? I can't do work to compress the gas. Work can't be done by the gas as it expands. So what I have here is the work is equal to 0, which means the change in internal energy is equal to the heat added. No work is done. And so any heat added is going to increase the internal energy of the system. Any heat taken out is going to decrease the thermal energy of the system. Now, if we look at all of these changes together, in an isochoric change, pressure, volume remains constant, so it might start here and then the pressure increases to there, but the volume didn't change. And so the work done equals 0. In an isobaric change, we've looked at this graph, pressure, volume, pressure remains constant, and so the work done is this area here. Okay? Work done equals pressure times change in volume. And then if we go, and so this is isobaric, constant pressure. This is isochoric, constant volume. Then we go to that other system, isothermal. We looked at this graph, pressure times volume, and so the work done can't be calculated directly off of this without some calculus, but we still have work done equals area under curve. Okay. Now, the last one is that adiabatic one. So let's take a look at the adiabatic system. And so imagine over here I have my piston and my cylinder. My gas particles are in there. Now remember, in the adiabatic one, that means that no heat flows into or out of my system. So imagine that this thing rapidly expands. So I went from a pressure that was high to a pressure that is fairly low on my curve. Okay. But that's not the only change that's happening. The temperature is also going down. So not all of the work that was done went into pushing this cylinder or the piston up. Some of that work also, or some of that energy was also a temperature change. So in an isothermal change, when we go from a high pressure to a low pressure, we end up following a curve that's like this. In an adiabatic change, we end up following a curve that goes more like this. And if you look at the difference between those, on the adiabatic change, the area is less because not all of the internal energy or the heat or whatever was used to do work. Okay, when this thing rapidly expanded, some of that led to a change in temperature, some of it was also some work done. But if it expanded isothermally, then all of that went into doing work. So the isothermal includes all of the work of the adiabatic plus this work here that wasn't used on temperature change. So the work done is still the area under curve, but it's less than the work done in an isothermal thing. The change is more rapid, so there's also some temperature change. So temp change and work done. Okay. So both of those can happen in an adiabatic change.